Again, welcome to Unit 1 IP assignment lecture slides here. In these lectures, we are going to discuss about the numbering system. For example, how to convert octal, decimal, and binary, and also hexadecimal numbering system. Again, this is ITCO341 class. So our main objective is converting binary to decimal, also converting octal to decimal, hexadecimal to decimal, and also the opposite, converting decimal to both binary, octal, and also hexadecimal. So the first thing we want to know here is what is a numbers? We know we have natural numbers. Natural numbers can be 0 and any number obtained by repeatedly adding 1 to it. So a natural number can be, again, any number. So for example, here we have 0, 100, 32, any number we can think of. We know negative numbers are normally numbers that are less than 0. So example, we have negative 24, negative 1, etc. Then we also have integers. Integers are natural numbers. And also it can be a negative number or it can be also 0. So integers basically is a whole number. Example would be 600 or 0 or negative 600. Then the rational numbers normally looks like a quotient, a division, most of the time. So here we have a rational number 37 or negative 2/5. Also, it can be negative 1 or negative 249. Now, let's start with the concept of adding natural numbers. Again, we know this for a long time, but this is just a simple example. So, for example, if I have 642, we want to know the position of the zeros. For example, we know 6 here have 2 places, so it will be in the 100 position. 4 is in the only 1 place, so it will be 40 or 10 position. Then 2 will be a single unit. So 642 is the same as saying 600 because I have 2 digits here, plus 40 because I have only 1 digit, plus 2. There's no any other digit. So we say 600 plus 40 plus 2. So again, 642 means 600 because 600 is in the 100 position, plus 40 because 4 is in 10th position, plus 2 because 2 is a single unit. So this is a decimal value, and we normally use the 10 base 10. A decimal value, which is our regular numbers that we human beings know, is base 10. And the reason why it's base 10 because it has 10 digits from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's equal to 10. So a decimal number, actually, that's why it's called decimal, because dec means 10. A decimal number, the base is 10 because it has 10 digits. And that's what we say. The base of a number determines the number of digits and the value of digit positions. So if a decimal number have a base of 10, that will determine that a decimal number have 10 digits from 0 to 9. Then the positional notation is very important. We just did the example of 642 and one more time. So we can see we have 642 here. We said 642 is the same as 600. So that means it's 6 times 10 to the power 2, which is 6 times 100, which is 600. Then 40 or 4 have one more digit in front, so it will be 4 times 10 to the power 1. 2 is a single unit, so it will be 2 times 10 to the power 0. We know 10 to the power 0 is 1. So when we add all these values, we get 642. Now the concept of 10 to the power 2, 10 to the power 1 will help us to know how to convert, for example, a binary number to decimal, or hexadecimal number to decimal, etc. So this is just a foundation which we already know this. So here this number is in base 10. The reason why it's base 10 because we have 10 digits. 642 is base 10. So we raise it 10 to the power 0 because that's the first. We call the two position as the lowest significant bit. That's the lowest bit. The highest bit here will be 6. So 6 will be the most or highest significant bit. So that's why we say the power indicates the position of the number. So always the position of the number starts from the least significant bit and always start from exponent of 0. So that's why we have 0. The reason why we are using 10 because it's a decimal number. Now, if it's a binary number, we are going to use 2. 2 to the power 0, 2 to the power 1, 2 to the power 2, based on the position of the digit. Binary numbers will be 1, 0, 1 zeros. Now, if it's a hexadecimal, then we say 2 times 16 to the power 0. Since we know the hexadecimal have 16 digits and some alphabet, the alphabet are from A to F. So if we combine 0 to 9 and A to F, we get exactly 16 bits. So that's why the base is 16. So here, another example, the same 642. So we say 642 is the same as saying 6 times 10 to the power 2 plus 6 times 10 to the power 1, which we normally don't write the 1, plus 2 times 10 to the power 0, but 10 to the power 0 is 1, so we don't need to write it. So finding the solution here, again, please follow my cursor. Finding the solution here, we get 642. So the formula will be, this is again decimal number system, or it can be any number system. It will be r to the power, this will be the position of the value. So r, n minus 1. The reason why it's n minus 1, we can look here. We have 3 digits, but we have 10 to the power 2, not 10 to the power 3. And the first digit, we start from 10 to the power 0. That's why second becomes 10 to the power 1, 10 to the power 2. So that's why you see that the most significant value still will be n minus. So if n is 6 digits, then to be n will be 5. If the base is binary, then 2 to the power 5 times the digit itself. So this will be the digit. This will be the base and the exponent. And also the same thing here, we have the base and exponent. Here we have only r because we assume it's r to the power 1. That's the second digit, D2. D1, normally we don't write it because r to the power 0 will give me 1. So D1 always will be the same value. So we say r is the base of the number, and n is the number of digits in the number. So if the numbers are 3, then it will be 3 minus 1 will be the last. We have 3 digits, so 3 minus 1 is that, so 10 to the power 2. So D will be the digit in the ith position. So for example, here D is 6, 4, and 2. R, actually we start with first R here to the power 0, but we know anything to the power 0 is 1. This will be R, n minus 2, then minus 1. So what if 642 has the base of 13? The same concept, which means, again, the base of 13 means the value here is not a decimal number, it's a 13, I would say 13 number system, or the base. So this means we have a digit from 0 to 12, which make it 13. So if I want to convert this number, the same thing we do, the same process. The only thing that we change now, instead of base 10, we are using base 13. So it will be 13 to the power 0, the least significant bit, which is 2. 4 will be 13 to the power 1. Then 6 is in the third position, so it will be 13 to the power 2. Why? Because it's to be 3 minus 1. n is 3, third position, minus 1. So you can see here our answer changes now. We get 1068 in base 13, because you get 6 times 13 to the power 2 is 1014. 4 times 13 will give me 52, and 2 times 1 will give me 2. So we had all this value, we get 1068. Again, here it's supposed to be 1068 in base 13, not base 10. Base 10 means this will be 10. And actually base 10 will give us the 642. So that's why we say 642 in base 13 is equivalent to 1068 in base 10. That's in base 13. We are converting it to decimal. Okay, so the next we go to binary. In binary, we already know decimal again, the base is 10, because what? We have 10 digits from 0 to 9. In binary, that's why it's called binary means base 2. Base 2. So binary number system have only 0 and 1, 0 and 1, which is base 2. And this is the language that the computer understands. So here we say for a number to exist in a given base, it can only contain the digit in that base, which range from 0 up to, but not including the base. So we say, what bases can these numbers be in? It can be any base, so 122, 198, 178. So bases higher than 13, how are digits in bases higher than 13 represented? We say with a distinct symbols for 10 and above. This is where hexadecimal will come. Because when we say base 13, we know in English, the possible digit we have is 10 from 0 to 9. So we are going to add A, B, and C, because C will be our 13th position, which is 12. But we start from 0 to 9. It's 10 digits, but the last value is 9 because we start from 0. So the same thing if I have A, B, C added, total number of digits and the letters will be 13. But the last value C, it will be 12 if we are using the number system. So we're going to see example now. So for example, in base 16, it means all the values and the alphabet here characters should give us 16. So we can see from 0 to 9 is 10. A, B, C, D, E, F is 6. So 10 plus 6 is 16. But again, since we are starting from 0, the actual value for F will be 15, because from 0 to 15 is 16 digits. A will be 10 because we move from 9 to 10. B is 11, C is 12, D is 13, E is 14, and the last F is 15. So now converting octal to decimal. Octal means base 8. So the digit will be from 0 to 7. Base 8 from 0 to 7. So here the question says, what is the decimal equivalent of the octal number 642? Now, previous example, we are assuming 642 is what? Is decimal number. So we use base 10. We also assume it's 13. So we use base 13. Now we know octal is 8, so we have to use base 8. So this will be the converting octal to decimal. We multiply the first digit, that's the most significant. First, I know it's 3 digits, so the first digit will be 2, the exponent. So it's 6 times 8 to the power 2, plus 4 times 8 to the power 1, and the last digit, the least significant, always the base is, the exponent is 0. The base and the base is 8, but the exponent will be 0. Second value, the same base, but the exponent is 1. Third value, the same base, but the exponent is 2. We saw the formula with the exponent, always it will be n minus 1 value, 1. So if you are in the first position, 1 minus 1 is 0. 2 minus 1 is 1. 6 is in the third position, so 3 minus 1 is 2. So that's why we have 2 for the 6. I'm talking about the exponent, 2. 4, the exponent is 1 and 0. Now we multiply all the values and we get 3, 8, 4, 3, 2, and 2, and we add all together. So this means 642 base 8 is the same as 418 base 10. Again, converting octal to decimal. Next, we're going to convert hexadecimal to decimal. Remember, hexadecimal, there's a little bit trick, and I won't say it's a trick. It's just that the possible digit we have is from 0 to 9, which is 10. So A to F, make it 16 together. X means 6, this means 10. So hexadecimal means we have a 16 base. The base is 16. Now, a question is given, what is the decimal equivalent of the hexadecimal number? We said again, A is 10, B is 11, C 12, D 13. So this number I'm saying here, D, E, F, in my head, if I'm going to do a calculation, I will assume D is 13, E is 14, F is 15. Now we are converting this, our number, to decimal. Now, the first thing, as we said earlier, remember that the digits in base 16 are from what? 0 to 9, then A to F. A is 10, F is 15. So it's like 10 to 15. So from 0 to 15, the total digit, again, they are 16. So the base is 16. So now let's start the conversion. Remember we did the decimal, the base was 10. When the number was given in octal, and we want to convert it to decimal, we use the base 8. Now the number is given to us as a hexadecimal. We want to convert hexadecimal to decimal, we use base 16. So here we get a D times 16 to the power 2. Why 16 to the power 2? Because D is in the third position. So the exponent will be 3 minus 1 for third position. Y is in second position. The same step. You can see that converting binary, hexadecimal, octal to decimal, the steps are the same. What changes is the base value. So assuming D is, actually that's why we convert it now. D means 13, Y means 14, F means 15. Since 15 is a single unit, it will be 16 to the power 0, which is 1. So we add everything. So our final answer will be, if I have D, E, F base 16, and I convert it to decimal, my answer will be 3567 in base 10. So any value you write. Now, in our assignment, we have one question that we have to, I think, add 2 decimal numbers, or even find the difference of 2 decimal numbers. What you can do first, you can convert the hexadecimal to decimal, both numbers, before you do your arithmetic operation. Otherwise, you get the answer wrong. I think it was subtraction. So for example, if I have DEF minus AB, convert both DEF and AB to decimal number system, then subtract it. Don't try to subtract two hexadecimal numbers direct. So next is converting binary to decimal. And the same thing, we know binary numbers are what? 10, 10, 10. So this is example given. The same thing now, we have to use the base 2. Binary number, the base is 2. And the same step, we have to start with the least significant value, the 0 here, the exponent will be 0. So it will be 2 to the power 0. First position will be n minus 1, so 2 minus 1 is 1. So it will be 2 to the power 1, 2 to the power 3, all the way to the end. So this is what we get. How many digits? Since I saw 2 to the power 6 here, it means we have 7 digits. So let's check. 1, 2, 3, 4, 5, 6, 7. Yes. So here again, it's up to you. You can start with the least significant bit, or you can start with the most significant bit. They are all the same. So here we are starting with the most significant bit, the 1 here. So 1 times 2 to the power 6 plus 1 times 2 to the power 5 plus 0 times 2 to the power 4, which is this. The 4 because it's in the 5th position. 5 minus 1 is 4. 1 times 2 to the power 3, 1 times 2 to the power 2, 1 times 2 to the power 1. And the last least signal, we always start from 0. So 0 times 2 to the power 0. We multiply everything, then we add all together. So after that, we get 110 in base 10. So binary number 110, 1110. When we convert it to decimal, it will be 110. So we can see that again, the steps are the same. So next, let's go to arithmetic in decimal. Here we say, how do we add two decimal numbers? We say 197 plus 265. We just add them straight. For example, 7 plus 5. We can arrange it in vertical. Then we get 7 plus 5 is 12. So I write down the 2 remainder 1. 9 plus 6 is 15 plus 1 is 16. So I have 6. And remainder 1. And then I will get 462 because 1 plus 2 is 3. So the answer will be 462. We know this. That's why actually this slides we didn't write the answer. Everybody know this. Now remember that there are only 2 digits in binary. So if I want to do the binary arithmetic, I have only 0 and 1s. The rule said 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. But 1 plus 1 is 0 remainder 1. But 1 plus 1 plus 1 will be 1 remainder 1. So here, let's see. So we are given 2 binary numbers. Again, the top with the arrow section are the remainders from the previous. But what we are doing, we are adding 1100, let's say 10101111 plus 10010011. So we are adding these 2 binary numbers. So we start with this section. Again, follow my cursor, my mouse cursor here. So I'm starting with the last or the least significant bit. So I will get 2 here in actual arithmetic operation. If it's decimal, it's 2. 1 plus 1 is 2. But again, this is binary. So binary, as we said earlier, the rule said 1 plus 1 is 0 remainder 1. So I write 1 plus 1, 0. Then I write the remainder 1 here at the top. Then 1 plus 1 plus 1 will be 1 remainder 1. So I write the 1 here and the remainder 1 is here. Then 1 plus 0 is 1 plus 1 will be 0 remainder 1. So 1 plus 1 is 0 remainder 1. So I put 0 remainder 1. And the same thing we have 0 here. So it will be 1 plus 1 again, 0 remainder 1. We still have 0 here. So it will be 1 plus 1 again, 0 remainder 1. This time here, we have only 0, 0. So here we say, okay, 0 plus 0 is 0 plus 1 will be 1. Then the last section will be 1 plus 1 is 0. Then the remainder 1 will bring it forward. So the rule here is that 0 plus 0, this is binary arithmetic. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is still 1. But 1 plus 1 is 0 remainder 1. Then 1 plus 1 plus 1, 3 ones will be 1 remainder 1. And those are the simple rules we use here. So those are the carry values, the remainders. Now, subtracting decimal numbers. Let's say this is a decimal number. We know how to do this, so we didn't even write the answer. 271 minus 196. 1 is less than 6, so I have to borrow 1 from the 7. And it will be 11. So 11 minus 6 will give me 5. Now I have 6 here alone. 6 is less than 9, so I'll borrow 1 again from 2. So it will be 16 minus 9, which will give me 7. Now, since I borrow 1, this will be only 1 left. 2 will be only 1 left. So 1 minus 1 is 0. So the answer will be 75. because 1 minus 6, 1 is less, so we borrow 1, we get 11. 11 minus 6 is 5. Then we have 6 here now. 6 is less than 9, so we borrow 1, we get 16. 16 minus 9 will give me 7. Now I have only 1 left at the 2 since we borrow 1. So that will give me 1 minus 1. So the answer will be again 75. Now, we can do the same thing for binary subtraction. Actually, we have a question like this in our assignment. Remember the sign numbers, 1 stands for negative, 0 stands for positive. So here we have 2 binary numbers, and we are going to subtract. So we know the rule said 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 0 is 0. So those are the rules we're going. So 1 minus 1 is 0. 1 minus 1 again, 0. 1 minus 0 is 1. Then here we have 0 and 1. But since 0 is less than 1, the same thing we did in decimal subtraction. Since 0 is less than 1, I'm going to borrow 1 from here. So if I borrow 1 to 0, it will tend to 2. Again, that's how binary number system is. If it's decimal, if I borrow 1 to 0, it will be 10, 1, 0. But here, borrow 1 into 0, that will give me 2. Now, 2 minus 1 will be 1. Now, remember this is 0 now, actually, that's why we have the 0 here. So then this is 1, so I have to borrow 1. So I'll borrow 1 from this one here, and I'll borrow 1 again down here. So this time it will be 2 again, minus 1 will give me 1. Remember here is 2, and we borrow 1 to here. So this means we have only 1 remain. So 1 minus 1 will give me 0. And here we already borrow 1 already. So it's 0 left. So it will be 0. So one more time, we are subtracting 1, 0, 1, 0, 1, 1, 1 from, 1, 1, 1, 0, 1, 1. So subtracting 1, 1, 1, 0, 1, 1 from 1, 0, 1, 0, 1, 1, 1. So 1 minus 1 is 0. 1 minus 1 again, 0. 1 minus 0 is 1. But 0 minus 1, 0 is less. So I'm going to borrow 1. Unless we don't have any value here to borrow, then we are assuming the answer will be negative as this thing, decimal number system works. But since we have 1 here, we borrow 1 to 0. But if I have 0 and I borrow 1 to it, it will be 2. So it will be 2 minus 1 is 1. Actually, that's why we write the 2 down here. Now this is 0 again, but we have 1 in the front. If we don't have 1, then we say the answer is negative, whatever we get. But since we have 1 in the front, we borrow 1 to the 0, that is 2. Then we take 1 out to borrow it, that's 2, because this is 0. So 2 minus 1 is 1. Remember this 10 to 1 now because we borrow, it was 2, but we borrow 1. So 1 minus 1 will give me 0. And here we already borrow it, so this is 0, so we just write the 0. So this is again counting the binary octal decimal number system. So we can see binary start from 0, 1, 1, 0, 1, 1, 1, 0, 0 is 4, and for decimal also is 4. Decimal will end at 9, the digits. Then we start from 1, 0, 1, 1, 1, 2, all the way to 190. Then we start from 2, 2, 0, 2, 3. Octal normally we end at 7. Then we start from 1, 0, 1, 1, 1, 2. We go up to 1, 7. We can't go 1, 8. Then 1, 7, you come to 2.0. Binary, straightforward, is only 2. So 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. Keep going. So again, we're doing converting binary to octal. Now here, there's no decimal. But if we like, there's 3 steps we can do. If I'm converting binary to octal, we did already how to convert binary to decimal. So I can convert binary to decimal. Then when I get the decimal value, I'll convert the decimal to octal. You get the same answer. But again, we know that octal always have 3 binary digits. So if this binary number we are converting to octal, we start from the least significant value, partition it into 3. So you see we get 0, 1, 1, then 1, 0, 1, then 1, 0. 1, 0 is the same as writing 0, 1, 0. So from the table, we saw that 0, 1, 1, the octal value is 3. 1, 0, 1, the octal value is 5, and 1, 0 is 2, which we can go back 1. So this is why we should know this table. If I'm looking for octal 7 to convert to binary, I know it's 1, 1, 1. So we saw 6, 6 was 1, 1, 0. Then 4 is 1, 0, 0. And then 2 octal will be 1, 0. So that's what we did here. So our final answer will be 253 base 8. We are converting it to octal. Now, if I'm converting binary to decimal, then we saw that example already. We use the base 10. So now converting binary to hexadecimal. This is different from decimal. If I'm converting decimal to hexadecimal, I will use the base 16. But now we are converting binary to hexadecimal. Hexadecimal with binary, we can partition the binary number into 4 digits. So the same question, but you can see that this time we make it 4 digits. 1, 0, 1, 1, 1, 0, 1, 0. So from the table, we can see that 1, 0, 1, 1 is the same as 11. 11 is B. Then 1, 0, 1, 0 in decimal is almost the same as 10, but in hexadecimal 10 is A. So the answer will be AB, which is equivalent to binary number 1, 0, 1, 0, 1, 0, 1, 1. Or another option, convert the binary to decimal. The answer you get in decimal, you convert decimal to hexadecimal using the base 16. So these are the algorithm for converting number in base 10 to other bases. Now, base 10 means I'm converting decimal to hexadecimal. So in our question, converting hexadecimal to decimal is we do division. But converting decimal to hexadecimal, we do multiplication with the base. So divide the decimal number by new base, make the remainder the next digit to the left in the answer, then replace the original decimal number with the quotient. So converting hexadecimal to decimal, we use base 16 multiplication. But converting decimal to hexadecimal, we use division of 16. And this is an example here. So what is 1980? This is a little bit tricky, so always be careful. Now, if I'm converting octal to decimal, I will write the base is 8 to the least significant bit of exponent 0, then the next 1, then the next 2, etc. But if I'm converting now decimal to octal instead of octal to decimal to octal, we divide. So you can see here, we are converting 1988 to octal. So we divide by the base 8. Now, if the question given to us, we are converting octal to decimal, then we multiply by the base 8. It's also using the exponent of the position of each digit from 0, the least digit, to the highest digit, n minus 1. So here we divide. So when we divide 1988 by 8, remember the question here is converting 1988 base 10, so decimal to octal. So anytime we are converting decimal to octal, we divide by 8. Anytime we converting decimal to hexadecimal, we divide by 16. When you divide the value by 8, the possible remainders will be 0 to 7. When you divide the number by 16, the possible remainder will be from 0 to 15, which is F, from 0 to F. If you divide a number by 2, which means I'm converting decimal to binary, then I can divide by only 2. The remainder will be 0 and 1. So that's what we have here. 1988 divided by 8 will give me 248, remainder 4. Again, here we just do the long division process. but the actual answer will be 248 remainder 4. Our concern is the remainder value. So when we have the 248 remainder 4, the answer we have here, if it's greater than 8, we have to divide by 8 again. So we divide 248 by 8. We get 31 remainder 0. The answer we get here, 31, still greater than 8, then we divide 31 by 8 again. The answer is 3 remainder 7. Now see, the remainder is less than 8. So we keep the last 3 remainder. Even if we divide the 3 by 8, it will give us 0, and the remainder will be 3. So we keep the remainder. Now, since I'm dividing from my left to my right, when I'm going to write the solution, I'll write 3704. So 3704. I start the division and get my answer from left to right. So these are the remainder, 4073. But the answer will be from left to right, the least value. So even if you divide it upward, the last value, which is the lowest remainder, you combine them from down up. Or in this case, I'm dividing from left to right. So my answer will be from right to left, 3704. Now, if I'm dividing everything up, down, then I'm going to read the answer from down up. Or the opposite, if down up, I'm going to read the answer from up down. So always, your remainder, you read it opposite. So the next one, what is 3567 base 10 in base 16? So this means we are converting the same thing again, decimal to hexadecimal. Previously, we say octal, we divide by 8. Now you see that we divide everything by 16. The step is the same. Actually, this is the same as the previous example. We do hexadecimal to decimal, binary to decimal, octal to decimal. The steps are the same. Multiply the base. If it's binary, the base is 2 with the exponent. The exponent will tell you the position of the digits. We can see that for all the numeric system, the steps are the same. Here also the same thing, decimal to hexadecimal, we divide by any base it is. Hexadecimal is 16, so we divide by 16. So the question says we should convert 3567 to base 16 value. So we divide by 16, we get 222, remainder 15. We keep, anytime you divide the value by 16, the possible remainders will be from 0 to 15. So we keep the 15. Now, since 222 is greater than 16, we divide it again by 16. The answer is 13, remainder 14. But since 13 is less than 16, I'll keep the remainder 13 there. Now, if I'm going to write my answer, don't write 13, 14, 15, because we know in hexadecimal, 13 means D. So the same thing as we did previously, since I'm dividing from left to right, I'm going to write my answer from right to left. So the answer 13 means D, 14 means E, 15 means F. So the answer will be D, E, F. From again, my answer is from, remainder is from left to right. So my answer, I'll read it from right to left. So binary numbers and computers, we know that again in computer system, only binary numbers, the computer, which normally we use the term machine language. We're going to do this in unit 5. So low voltage will be 0, high voltage will be 1. So in machine language, all the bits we have is either 0 or 1. And in a computer system, we store values, symbols, etc. as byte. So 8 bits represent 1 byte. That's why when you go to a computer store to go and buy a flash drive or any storage device, you'll see that they will measure it in bytes. For example, gigabytes. Gigabyte means I can be able to store 1 billion characters, since 1 byte represents a character or digit or symbol. So 1 gigabyte means I can store either 1 character, digit, or symbol in the flash drive. So we are now familiar with the decimal number system base 10, and also octal base 8, and hexadecimal base 16. The characteristics of numeric system, we say the digits are always consecutive. The number of digits is always equal to the size of the base. So as we said earlier, and the number of digits. So if it's the digit is only 2. Binary, the base is what? 2. Decimal 0 to 9, 10, so the base is 10. And 0 is always the first digit in any numeric system. The base number is never the digit, because if the base is 10, we go from 0 to 9. If the base is 2, it's only 0 and 1. If the base is 8, only 0 to 7. So basically, this is all the characteristics of the numeric system. So hope this lecture will help us to convert numbers from decimal to octal, binary, and hexadecimal, or the opposite, from other octal, hexadecimal, binary to decimal. And again, wish everybody the best. Thank you. If you have any question about the assignment, again, you can contact me. Thank you.